Good afternoon, everyone. Can you see my screen?
Yes.
Thank you. First, I have posed the solution for homework 2. You can compare the solution and with your answer. Second announcement is about the exam 2. The exam 2 will be available next Thursday and next Wednesday and next Friday. You also have 2 hours to solve the exam 2. The exam 2 will only cover the topics from chapter 12. And starting for today, we will go back to the chapter 1 of the textbook. We will introduce some basic computer concepts. And for today's lecture, we have 2 slides. We will not go over the supplemental slides. You can read the supplemental slides by yourself. And the supplemental slides is from Dr. Lim. For today's lecture, you should read the textbook for sections 1.1 to 1.3. Then let's go back. Let's go to introduce the basic concept of the computers. So only the first 3 sections will be required from the chapter 1. So first we need to differentiate 2 concepts. What is the computer architecture and what is the computer organization? First, let's see the computer architecture. Computer architecture specifies some attributes of our system which are visible to the programmer. So when we talk about the computer architecture, we are focused on the attribute which are for the programmers, for the professionals. The computer architecture has a direct impact on the logical execution of a program. So what is the computer organization? For computer organization, the organizational units and their interconnections that realize the architecture specifications. So for computer architecture, we have several attributes, and computer organization is just the units, the device, and interconnections to implement the architecture. Then let's see some architecture attributes. The architecture attributes including the instruction set, the number of bits which are used to represent the different data types. For example, in modern computers, the int type, we will use 32 bits. For the char, we may use 8 bits. For the float, we may use 64 bits. And for the double type, we may use 128 bits. This is for different type of the data. We use how many bits to represent one data. The architecture attribute also including the input-output mechanisms and techniques for addressing the memory. Addressing the memory means we build the memory address. How do we access the data in that memory? These are the architecture attributes. Let's see some organizational attributes. For the organizational attributes, the hardware details are transparent to the programmer. So when we write any program, such as when we write a Java program, we do not need to care about the hardware details of the computer. We only focus on the top level, the high level language Java. And this Java program can be executed on multiple machines. The organizational attributes also include the control signals, the interface between the computer and the input-output devices, and also the memory technology used. So this is the computer architecture and the organization. Then let's see the structure and functions about a computer. A computer is a very complex system, and usually we design and implement a computer with the hierarchical system. The hierarchical system means we have a set of interrelated subsystems. Later, we will see a figure about the hierarchical system. The hierarchical nature of the complex systems is initial to both design and the description. And the designer only needs to deal with one particular level of the hierarchy at one time. We do not need to deal with all the levels. One level at one time. And for each level in the hierarchy, we need to concern about the structure and the function. So what is the structure and what is the function? The structure is the way in which components relate to each other. The function is the operation of individual components as part of the structure. So every component has several functions, and how the components relate to each other, they are called the structure. We will show examples later. Then there are four basic functions for a computer. A computer can perform data processing, data storage, data movement, and also can perform control. Let's see each one. What is data processing? The data may take a wide variety of forms. We can store the data in many different forms. For example, we have the integer from the data type. We have integers, float, strings. And from where we can store the data, we can store the data in a text file, in a CSV file, the comma separated file, in an Excel file, in a Word document, also in a database. So we have many different forms of the data. And the range of the data processing requirement is very broad. So for the processing requirement, we need the arithmetic for the data's arithmetic operation. Sometimes we need the Boolean, we need sorting, we need search, and so forth. All of them are related to the data processing. And for the data storage, we have short-term storage and long-term storage. The short-term storage, we will use the memory and registers. For long-term, we can use the file system. We can use the database. Then let's see the data movement. About the data movement, we have a two-level movement. The top level is the movement between the computer and the input-out devices. The lower level is the data movement between the components of one computer. Here, the input-out devices, for example, the hard drive is one output device, and for the input, the keyboard is one input device. For the lower level data movement, we call them the data connections. And also, for now, we can store our data in the remote device. For the remote devices, for example, we can use the cloud to store our data. And the cloud we are familiar with, maybe the Google Drive, the Microsoft OneDrive, the Dropbox. So for all these clouds, they are called the data communication. we move the data from our local computer to the remote devices, to the remote server. The last function is the control. A control unit manages the computer's resources and also arranges the performance of the functional parts in response to the instructions. For the computer resources, we know that we have CPU and we have the memory and so forth. So the control needed to manage all the computer resources. I need to arrange the performance for each instruction. For example, when we need to get the sum of 1 plus 2, we need a control to know that the control will be that we need to do the addition. And for the addition, we can use the add. For the computers, we have the single processor computer and the multi-core computer. Here we use two different terms, the processor and the core. The single processor means this is very simple. We only have one processor, one core, and one CPU. For the modern computers are the multi-core computers. We will see later. First, let's see the structure for the single processor computers. So this is the hierarchy. This is top level, middle level, and the lower level. So from the top level, we will see a computer. And in the computer, we have several components. For example, the CPU, central processing unit, the system bus, input-output devices, and the main memory. Then let's see the details about the CPU. Then we go to the next level. For a CPU, it has the registers, ALU, arithmetic and logic units, internal bus, and the control units. Then for the control unit, we can go to another lower level. For control unit, it includes the sequencing logic, the control memory, control unit registers, and decoders. In the previous lectures, we have introduced the decoders for the combinational circuit. So from this figure, you will know why we will introduce these combinational circuits, because we will use them in the computer. Then let's take more details. Let's talk about more details about the four major components of computer: CPU, input-output, main memory, and the system bus. CPU is short for central processing unit. CPU controls the operation of the computer and performs its data processing functions. The main memory is just to store data for short term. When we restart our computer, all the data in the memory will be lost. So the main memory is a short-term data storage. The RO, or the input-output, this is just move data between the computer and the external environment. The external environment, such as the hard drive or the USB drive. Then let's see the system interconnection. System interconnection is the mechanism that provides the communication among CPU, memory, and the input-output. Provide communication among the other three components. And one system interconnection mechanism is use the system bus. Then let's focus on the CPU. The CPU also have four major components: control unit, ALU, register, and CPU interconnections. That's shown in this figure. Let's see each one. The control unit controls the operation of the CPU and hence controls the operation of the computer. The ALU, arithmetic and logic unit, perform the computer data processing function. So we can perform arithmetic operation. We can also perform the logic operation. The registers just provide internal storage for the CPU. The memory is the internal storage to CPU, but the register is the internal storage to CPU. One example about the CPU interconnection is the internal bus. You see from this figure, we have the internal bus. The internal bus will provide the mechanism for the communication among the control unit, ALU, and the register. Okay, let's talk about the control unit. In this figure, we have a lot more detail about the control unit. Let's see each one. For the control unit, we have the internal control memory is the internal storage for the control unit. Sequencing logic is to perform some logic operation. And register is also the internal storage for control unit, and decoder to perform the decoding. This is just a single processor computer. And for today's, I think all computers use multi-processors or multiple cores. So when we talk about the multi-core computer, we have three terms, which are the CPU, core, and a processor. And they are in this level. The processor is in the top level. Basically, a computer is a processor is a chip. Inside in one processor chip, we may have multiple cores. Of course, in the processor chip, we have other blocks besides the core. And for each core, you can think each core is like one CPU. Then let's see this term in the multi-core computer architecture. The CPU is the portion of the computer that fetch and execute the instructions. The CPU consists of ALU, control unit, and register we have talked about. And the CPU in the multi-core computer structure is referred as a processor for the single processor CPU computer. So for the single processor computer, we can think the CPU, the processor, and the core, they have the same meaning. But for the multi-core computer, they have different meanings.
Professor?
Yes.
What do you draw next to cores on the right?
You mean this one? Okay.
Yes.
For this one, this is the blocks for other functions. Maybe we can have the cache memory. For modern processors, we will have a cache, and we usually have L1 cache, L2 cache, and L3 cache. So a processor chip has many components, several cores, several cache memory blocks, and other blocks. Any other questions? Then let's go back to the to introduce the term about the core and the processor. A core is an individual processing unit on a processor chip. And the core may be equivalent in the functionality to a CPU on the single processor computer. For the core, we may also have some specialized processing units. For example, GPU is the CPU is the general purpose processing unit, but we may have some specialized processing unit. For example, we can have a processing unit just to do the operation for the vectors or for the matrix. If you need a processing unit just for operation for vectors or matrix, then we need to redesign this processing unit from the hardware level to make that the operation on the matrix is efficient. CPU is the general purpose. So this is the core, also called a processing unit. Then what is a processor? A processor is a physical chip with one or more cores. The processor is a computer component that interprets and executes the instructions. Actually, the instructions are executed based on in each core. So that's why we call the if a processor chip has multiple cores, we call this is a multi-core processor. So that's why we say we have the multi-core computer architecture. Because usually for some computers, we only have one processor chip, but with multiple cores.
Hey, Professor.
Yes.
Does each core have its own registers, or do they share registers?
Yes. Each core has its only register, because one core could be a CPU, so it has the only register.
Okay, so each core has its own set of registers, right?
Yes.
Okay.
Then on the processor chip, except the cores, we also have the cache memory. We may have multiple layers of the memory between the processor and the main memory. And this memory are called the cache memory. The cache memory is smaller but faster than the main memory. So the cache memory are used to speed up the memory access by placing in the cache data from the main memory that is likely to be used in the near future. So in the computer, except the processor, we also have the main memory. We store all the data in the memory. And if we know, for example, if we want to do 1 plus 2, first we need to get the data 1. Let's do this way. So for the first addition, we get the 1 and get 2 from the memory and get the sum, which is 3. Of course, for this 3, this new value, we need to store in the memory. But if we know that just after this instruction, we directly will use this value of A, this 3 value. We do not need to store this 3 in the main memory. We can just store this 3 in the cache memory. Because the cache memory is much faster than the main memory. So for some near future use data, we can store in the cache memory to speed up the computation or speed up the operation. And usually, we will have the multiple layer of the cache memory. We have the level 1 cache, level 2 cache, and level 3 cache. So we have L1 cache, L2 cache, and L3 cache. So L1 is closest to the core, then L2, then L3, and so forth. So let's see example. Suppose this is the motherboard of a computer, and on the motherboard, we will have several input-out chips. We have some main memory chips, and more importantly, we must have the processor chip. Here, for this computer, we only have one processor chip, but for this processor, we have 4 cores. We have 8 cores. So this is a multi-core computer, but not multi-processor. We only have one processor, but 8 cores. So this is the processor chip, except the 8 cores, we also have the cache. And in the processor chip, we have L3 cache. Then let's see each core. For each core, you can just think each core is a CPU. So we have the ALU, the register. Except that we also have the instruction logic, load and store logic, then L1 cache and the L2 cache memories. For both L1 and L2, we have the instruction cache and the data cache. Let's see more details. Let's see the components or the elements of a core. The instruction logic. This component will include the tasks involved in fetching instructions and decoding each instruction to determine the instruction operation and the memory location of any operand. For example, we want to get the sum of 1 plus 2. This is the instruction. And for the instruction logic, logic component, we need to determine that we will use the adder to get the sum, and we need 2 operands, 1 and 2. And we need to use the decoder to get the address of the memory cell where stores 1 and where stores 2. Then we have the ALU perform the operations, and we also have the load store logic. The load logic or store logic manage the data transfer to and from the main memory via cache. Now we have cache memory and the main memory. So the load logic will control the communication, the data transfer between the main memory and the cache memory. Then let's see the L1 and L2 cache. For both L1 and L2 cache, we split to the instruction cache and the data cache. The instruction cache will store the instructions for the near future. The data cache will store the data for the operand for the near future and the result. So for example, for 1 plus 2, this instruction, this will be in the instruction cache. Both 1 and 2 may be in the data cache. Then let's see a photo of a real motherboard. On this motherboard, let's see. Here we have two processors. This is processor 1, processor 2. And each processor have four cores. So we have two processors, two quad-core processors. Except the processors, we also need the main memories. This part are the main memories. These two parts are the main memory chips. And also, except that we need the input-output chips, RO interfaces. Here for the RO, we have the chips for the USB drive, for the VGA. Except that we also have some chips for the Ethernet. And also, we must have a clock for the computer. Yes, this is a very old computer several years ago. Then with the understanding of the structure and functions of computer, then let's see a real computer. Let's see the history of the computers. The first generation computer is based on the vacuum tubes. The vacuum tubes were used for the digital logic elements and memory. The first computer or first generation computer is called the IAS computer. IAS is just the computer name. When designing the IAS computer, the fundamental design approach is use the start program concept. We will start the program. And this computer is designed by Dr. Van Neumann. So that's why the architecture is called the Van Neumann architecture. And the Van Neumann architecture is the base of all the modern computers. So the IAS computer is the prototype of all the subsequent general purpose computers, such as the laptop and the desktop we use today. All the laptop, desktop, and the servers, they apply the Van Neumann architecture. So let's see the structure of the IAS computer or the structure of the Van Neumann architecture. In the Van Neumann computer, we have several parts. We have the CPU part, we have the CPU, we have the main memory, we have the control unit, and we also have the RO, input output. So there are four major components in the Van Neumann machines. And you may find this structure is very familiar because all today's computers use this same structure as the IAS computer. And all these machines are called the Van Neumann machines. Of course, for both CPU and the control unit, we have a different type of registers. We will introduce more details. So let's see the four components in the Van Neumann machine or the IAS computer. The main memory is to store the data and the instructions. Remember, the fundamental design approach of the IAS computer is based on the stored program concept. We will store the program in somewhere. And the program is the set of the instructions. So the memory stores both data and instructions. ALU, we are familiar with, operate on the binary data. Control unit is to interpret the instructions in memory and cause them to be executed. RO, which is operated by the control unit. Let's see the memory format. This is the memory format of the IIS computer. First, let's see more details. The memory of the IIS computer has this number of storage locations, and each location is called a word. In the IIS computer, a word has 40 binary bits. So in the main memory, both data and instructions are stored there. So we need to know the format to store the data and the format to store the instructions. And the data, at that time, at the IIS computer time, the most commonly used data are the numbers, not strings. Because at that time, we only use the computer for the scientific computations. So the number is the major data. And in IIS computer, each number is represented by a sign bit and 39-bit value. Each number is represented by one word. One word has 40 bits. So we just use the leftmost bit for the sign and the other bits for the value. So this is the format for the number word. And a word may contain 2 instructions. Then each instruction just use 20 bits. Among these 20 bits of each instruction, we split this 20 bit to 2 parts, 8-bit and 12-bit. The 8-bit is used to store the operation code. For short, we call OP code. The operation code is to specify the operation to be performed. For example, the operation could be the addition, could be multiplication, could be the AND operation, and so forth. Then the second part with 12 bits is just for the address. This 12 bit stores the address of one word in the memory. So based on this address, we can find the operand. For example, when we get 1 plus 2, this addition is the operation code. And we also need the numbers. So the address of these numbers was stored in this 12-bit address. So here, this is the instruction word. One word has 2 instructions, and for each instruction, we have 8-bit for the operation code, then 12 bits for the address of the operand. Then let's see some registers in the IIS computer. Here we have many registers such as AC, MQ, MBR, PC, RBR, RR, MAR. Let's see each one. The MBR is for the memory buffer register. Memory buffer register contains a word, 40 bits, to be stored in the memory or sent to the RO unit. Or the memory buffer register can also be used to receive a word from the memory or the RO. Here we see the memory buffer. When we see the buffer, buffer is just for the temporary use. Then we also have the memory address register, MAR. It specifies the address in memory of the word to be written or read from this buffer. We also have the instruction register IR, which contains this 8-bit operation code of the executing instruction. We also have the instruction buffer register. When we say buffer, this is just for the temporary use. We just store some temporary data. So the instruction buffer register is just used to temporarily hold the right-hand instruction from a word in the memory. We also have the program counter PC, which contains the address of the next instruction pair to be fetched from the memory. Then accumulator and the multiplier, quotient, AC, and MQ. They are used to temporarily hold the operand and result of the ALU operations. So when we execute an instruction, different part of the instruction will go to different registers. And for the memory and the instruction, we also have the buffer registers. So in this figure, we show a flow chart about how to execute the instruction in the IS computer. And in this flow chart, we just separate with this line. The above part is called the fetch cycle. The below part is called the execution cycle. To execute an instruction, we first need to fetch the instruction from the memory to the control unit. And then we will execute this instruction. The IIS operates just by performing the instruction cycle repeatedly. And this entire figure, this entire flowchart is called a instruction cycle. So instruction cycle has two subcycles, fetch cycle and the execution cycle. During the fetch cycle, the operation code of the next instruction is loaded to the instruction register, and the address portion is loaded to the memory address register. We just fetch the instruction and make the next instruction is ready to be executed. Then when the next instruction is ready, its OP code is in the instruction register, we will go to the execution cycle. Execution cycle is just to interpret the operation code and execute the instruction. The result of executing an instruction may have two effects: either move data or perform an operation by the ALU. We have talked about the instructions. Here we give the table about all the instructions used in the IIS computer. And among these instructions, we have several, 1, 2, 3, 4, 5. We have 5 groups: data transfer instructions, unconditional branch instructions, conditional branch instructions, arithmetic instructions, and address modify instructions. For each instruction, we have the operation code. For this column, we also give the symbolic representation. The symbolic representation is like the assembly language. Actually, in the machine code, we use the operation code. But for us, for human beings, we can use this column, the symbolic representation, and also we have the description for each instruction. Let's see each group of the instructions. In IIS computer, there are totally 21 instructions. The data transfer instructions are used to move data between the memory and the ALU registers, or between two ALU registers. the unconditional branch instructions facilitate the repeative operations. Because we will execute the instructions in the sequence. For example, we have the instruction 1, instruction 2, instruction 3, instruction 4. We will execute these instructions in the sequence. First, instruction 1, then R2, then R3, then R4. But in the programs, in the program control flow, we have three types of the control flows. First is the sequential execution. By default, we will execute the instructions or the code in the sequence. Except the sequence, we also have the loops. And we also have the branches. The if, else. So for the loops, we can use the while loop or the for loop in the Java. For the condition, for the branches, we can use the if and else. So by default, we execute the instructions in the sequence. So we have the flow for the sequence. But how do we get the control flow for the loop and the branches? Here, this unconditional branch instructions is used to implement for the loop operations, for the loop behavior. For example, let's see. One unconditional branch instruction is just a jump. Jump means we go to the one instruction. For example, maybe instruction 3 is jump to I1. Jump to I1 is after execute I2. When we execute I3, we will jump to the I1. We will go to execute I1 again. So here we jump to I1. We will have a loop, and in this loop, we can repeat execute the I1 and I2. So this is the unconditional branch. So we have done for the loop flow, but how about the if and else? For if and else, we need to use the conditional branch. It allows the decision points. So let's see here. For the conditional branch, we have this plus. Plus means for positive result. So maybe the conditional branch is like this way, R1, R2. Maybe the I3 is a conditional branch. So if positive, we will jump R5. So when we executing the third instruction R3, we have a condition, which means the data must be positive. If the data is positive, we will go to execute I5. If the data is not positive, we do not jump, then we just follow the sequence. So for positive, we use this branch. For non-positive, we use this branch. And the other two groups, arithmetic instructions are just operations by the ALU, the arithmetic operations or the logic operations. The address modify instructions, they permit the addresses to be computed in the ALU and then inserted into the instructions stored in the memory. With the address modify instructions, we can get the operation on the address, not just the data. We can manipulate the address, so it will allow the addressing flexibility. So far, you do not need to understand each instructions. Later, when we go to chapter 3, we will talk more details about the instruction set of computers. So this is the first generation computer, RAS computer, also Neumann computer. The following part are optional. The following part including the the embedded system, the ARM structure and the ARM architecture. Let's quickly go over the optional part. First, this is in this figure, this x-axis is the year, and the y-axis is the number of the transistors in the chip. We see the number of transistors in one chip is growing, and then for this observation, we have the very famous Moore's law. Moore's law is the observed number of transistors that could be put on a single chip was double every year. And this is the most recent observation. Actually, in the 1970s, this number of the transistors was doubling every 18 months, 1.5 years. So with the Moore's law, we have several consequences. For example, we have a low cost for the computer. We have the computer size is smaller, and the transistors in a chip is more. Except the general purpose computer, we also have the embedded system. Embedded system is a computer system which is used in another product. For example, for now, you may be familiar with the smart home. Smart home, this term, and in the smart home, for everything, for every device, for every appliance, for the TV, for the dishwasher, and for many devices, for many equipments, we have an embedded computer system. So this is the embedded system. Let's quickly talk about the organization of our embedded system. Of course, the processor is the core part of all the computer system. And for the embedded system, we need the human interface. And we also need the sensor, actuator, also the memory, the logic, and the diagnostic port. So for the sensor and actuators, we need AD convention and DA convention. Then for the embedded system, we also have another term which is called the Internet of Things. This Internet of Things term refers to the expanding interconnection of the smart devices, ranging from the appliance and to the tiny sensors. Of course, the Internet of Things may contain several components such as the information technology, operational technology, personal technology, sensor, and the actuator technology, and so forth. Then for the embedded system, we also need the embedded operating system. For the embedded operating system, we have two approaches to implement it. One way is we take an existing operating system and modify it and adapt it to the embedded applications. The other way is we just design the operating system just for the embedded application. About the processors used in the embedded system, we have the dedicated processors and the application processors. The application processor is for the general purpose. For example, the processor for the smartphone, for the cell phone is for general purpose. With the cell phone processor, we can do many things, just like a general purpose computer. But for some dedicated processor, they are just defined for some specific application in the embedded system. So we was in the embedded system, the processor is usually called the microcontroller. And for the embedded system, our processor is usually based on the ARM architecture. For the general purpose computers, our laptops, desktop, and servers, we will use the von Neumann architecture. But for the embedded processors, such as the smartphone and other devices, we will use the ARM architecture. The ARM architecture will use the is based on the RISC microprocessors. The RISC means reduced instruction set computer. So from the reducer, we know that in the ARM architecture or in the ARM processors, the supported instructions is fewer than the normal computers. Any questions?
Professor,
Yes.
there's one part where you covered like where I3 jumps to I5. What are these I's for?
You mean which part?
Previously, where you talked about after if else, I think.
You mean this part?
Before that, there it is.
Okay, for the control flow, when we write a program, we know that we have the sequence flow, the loop flow, and the branch flow, if else. So for these three kinds of flows, we also need the corresponding instructions to implement these flows. So for the branch, for the if and else, this flow, we can use these instructions. We can use the instructions from this group, instructions from the conditional branch group from this group. And here, for this group, we have two instructions for the IS computer. An example is here. Suppose the I3 is one conditional branch instruction. When the input number is positive, we jump to I5. So if the number is not positive, we do not jump to R5, which means we use the normal flow. Normal flow is a sequence flow. And in the sequence, we will execute I4. So for the I3, for the positive, if yes, we go to the R5. If no, we go to the I4. So this is the example why we can use the conditional branch instruction to implement the branch flow, the if-else flow. Any other questions?
So it's an example of the conditional branch.
Yes.
Okay.
For the chapter 1, you only need to know the terms or know the basic concept. And for some important topics such as the memory structure, such as the instruction set, we will talk more details later in the chapter 3 and so forth. Any other questions? That's all for today. Thank you.
Thank you. Bye.